So, gentlemen, thank you for tuning in for today's class on InfraLAB. InfraLAB simply means infrastructure. Okay, this course is a short course, weekend course that is meant to bring to speed all the potential infrastructure experts. And when I mean infrastructure experts, we are talking about people who are interested in water reticulation, sewer, stormwater, and road. The other ones are like telecommunication and electricity, which is not within the scope of this class. So we are just focused on those ones that we know that are related to water and infrastructure. So this is what we're going to be covering today. We've started by 10. The next 2 hours will be done. And today we're entering module number 2. And module number 2, we'll be talking about stormwater and sewage network design. And stormwater and sewage are the two components of the urban drainage system. In every urban drainage system, you have the sewer and storm. You have the sewer line and storm line. In some cases, you have what we call a combined system, but those systems are rare. And there are many found in developing countries where they don't have space. But 90% of infrastructure design is that the sewer line will be different. The stormwater line is different. The stormwater line is one you see in front of your house. Some people call it gutter in local parlance. Okay, it's just for you to convey the storm event, the storm water. Okay, based on peak flow, based on rainfall rain events. Okay, so you convey them through drains, then collect them through. Sometimes people build what we call primary sedimentation tank. Oh, okay, or they call it combined sewer overflow. There's no treatment whatsoever. Then from there, you take it to the open stream and open drainages, open river, and discharge them. No treatment. Okay, because they are not much contaminated. But the one that pass through your domestic use, okay, they have undergone interaction with human activities. Those ones need to be conveyed most times through underground pipes, which most times are also PVC pipes with limited diameters. And they are conveyed to a central wastewater treatment plant. But due to our level of development, people have what they call septic tanks. So instead of a pipe running hundreds of kilometers to a treatment plant somewhere, it simply runs from your room, from your kitchen, to your backyard and enters a septic tank, and sometimes a sock away. Okay, so that is your own domestic wastewater treatment plant. But in developed countries and in developed areas, and in the future, those things might not be applicable. I've already seen estate development talking about having a centralized wastewater plant, because based on the principle of circular economy, everything is a circle. So if you're able to recycle your waste, let's say you eat a food worth 1,000 naira, and you're able to recycle it, you can reduce 200 your wastewater, and you can use it to generate biogas. Okay, from biogas you can generate methane, which you can use to produce with a methane generator. You can produce electricity. Then the waste that is remaining, you can incinerate it and use it to burn one or two things. Then the ashes that remain, you can use this as a fertilizer. So you can see that this concept of circular economy is something that is part of also what we are discussing. But so far, our designs have not been very sustainable. We just put our waste in the sock-away pit and then allow them to go. And we don't even have any recovery mechanism. And that is not good, because you can recover at least 10 to 20%, and that is quite much. Okay, so back to what we're saying. So there are two systems in every wastewater system, any urban drainage systems. Okay, one is what I call the stormwater and the other one is the sewer. The sewer network usually goes underground. It usually conveys wastewater from human activities to a treatment plant or a local soakaway septic tank. While the storm sewer will run hundreds of kilometers until they get to an open drain, and then they discharge into an open drain, open river, sorry, or open water body. Yeah, that's where they discharge. So I want you to get the distinction of these two, and so that you know that in every urban design, there are two things you need to take care of. Okay, so I'm trying to open one or two PDF, and I don't know what is happening. So the thing we're going to do today is we're going to take an overview of the hydrology and the hydraulics. The hydrology and the hydraulics. Now, our end result is going to be the hydrology. The hydraulics, sorry, that's our end result. Then our input parameter is going to be the hydrology. So you give me the hydrology of the network, the hydrology of the area, I can give you the hydraulics. Then you also give me the water intake, okay, of the people. What is their water consumption? I also give you the wastewater production, you know, the law of continuity, or the Langerian principle. Anything that comes in is what goes out. Okay, so if I consume 100 liters of water in a day, I mean, you should expect me to produce also 100 liters. So that is the baseline for me getting my intake parameter when I want to design my sewer system. But for the storm system, I have to look at the hydrology of that area, which is basically saying the storm activity. Okay, what is the rainfall intensity per hour? That will lead me to how to design the hydraulics of my storm line, storm sewer, storm network, or drain. One thing about this course we're doing today is that people use these words interchangeably. Somebody can tell you to say drain. When somebody says drain, please, what comes to your mind should be storm drain. That's what people refer. When somebody says drain, it should be storm drain. So if someone is trying to refer to the one that has a high BOD, the one from human activity, that should be sewer. But some people sometimes we also say storm sewer. They are also correct, because sometimes in the developed country, their storm sewer runs underground. Places like New York, some places like in Abuja, okay, some places in well-designed British during colonial time, some of the cities that were designed, some of their drains are underground. So one can also say storm sewer. Okay, sewer is basically like a pipe, concrete pipe or PVC pipe, definitely not iron or asbestos pipe that will convey liquid. So it depends on now what is conveying, whether it's conveying foul liquid, which is foul sewer, or it's conveying storm sewer, okay, or storm liquid coming from rainfall. I'm taking my time to explain these two because many people confuse the two. And it is difficult for you to understand what you cannot differentiate. I mean, the first step of everything is for you to have a grasp of that thing, have an understanding of the concepts. Okay, if you're looking at what is on my screen, on my home page of my slide, that is definitely not sewer. It can be. You hardly see sewer in open drain. That was 40, 50 years ago in Europe. Places like Rome, places like this Germany that you see that are beautiful now. Gentlemen, the way you see this water being discharged, that's how they discharge their waste. Before they wake up and knew that this thing is causing death, it's causing cholera, it's causing dysentery, because any slight opportunity, this thing will enter into human consumption, and that will lead to E. coli, infestation, which will lead to definitely you must get sick. So I hope I've been able to make that distinction. I'll try as much as possible to also go further and try and make those distinctions as we go on. But I have no doubt that everybody's on the same page. Any question on that? No question. No question. So where do I start from now? So that I will consolidate on the examples I've given. So today, let's start with sewer. Let's start with sewer. So now sewer systems. Of course, as I said, it can be storm sewer, it can be just hold on. Please, any question while I'm waiting for this thing to open? Okay, good. Here we are. Let me open on the slides. It's a particular slide I'm looking for. I will really drive home the point I'm trying to make. Here, I think it's more like this one. Stay with me. Okay, I think I can start with this urban drainage. So let's talk about urban drainage. Design of sewer systems and storm treatment. Now, that word storm treatment, I want you to be careful with it because it's not everywhere that you treat your stormwater. When we talk about treatment of stormwater, it's basically when it is highly contaminated, maybe it's coming from unrecognized areas, maybe industrial areas, then you needed to hold it to a holding body. Okay, you collect it and hold it somewhere, then it will decant. Okay, the clear water, the top will be clear. Then that clear water, you discharge it. Then the bottom one, you either use it for agricultural purposes and dry it, or you take it to wastewater treatment plants. But the one that requires treatment, the one that you cannot discharge in open drain is your sewer. It is absolutely not acceptable for you to discharge your waste sewer, your sewer, your foul sewer into open water body. I'm aware that some people do it, but it's wrong. Some people do it in local areas where they go and they defecate inside open street, or they channel their wastewater pipe from their houses. You channel it into an open drain in front of your house. Please, if you are guilty of that, it is wrong because the implication is this: simple. Once you empty it, maybe nobody's seeing you as at the back of your house. Okay, what you need to realize is that once it goes into an open body, there are people who need it downstream, hundreds or thousands of kilometers away. When you see any river passing through your place, that's not where it ends. Okay, some people you need it downstream. Okay, you're raising your hand. Or is it a mistake?
Yes. No. It's not a mistake, sir. Just to buttress that point, you mentioned the fact that mixing stormwater and sewer is wrong.
Yeah.
And in my years of working, I noticed, especially in a place like Guzape in Abuja, apologies to those who are not based in Abuja, I noticed that they have that issue. Wow. You get to a site, the plots are serviced, but you'll find only stormwater service manholes. So a lot of people are forced to pipe both sewer and stormwater into the same point.
Wow.
Guzape.
I see that authorities should be alerted. Yes. See, that's not the first time I'm hearing about this, but this is ignorance, is wrong. Guzape is an issue. I don't want us to discuss. Guzape is a very big issue. It's a failure of governance. But that's by the way. I think what they have made, so there should be some, maybe it's a mistake, sir. People are mistaking the two. I strongly believe that Guzape should have a sewer line. Because
they
Guzape,
do.
Okay.
They do, but from Well, let me explain, because some years ago, maybe around 2016, 2015, 2016, when I was doing a project, we got to the point where we needed to connect the sewer. Okay. And what we were told is they had not completed the sewer line.
Yeah.
So
aware of that. Some areas.
The project was held up because of funds.
Yes.
So they had not completed it.
I'm aware.
You know, there was a lot of pressure on the government to open up the area for development.
I know. I say it's a failure. Go ahead.
Yes. So because of that, this thing that I'm talking about, I was in one of our other projects there last week. It was the same thing. We looked for sewer line, we didn't find.
Wow. And you are forced to forced to make do what you have. What you got, sir? What's the pipe diameter? Let me make sure that it was a sewer line. What was its pipe diameter?
Definitely it's 200. The sewer line.
It's a sewer line.
Definitely. But the interesting thing is on the roads that have been done, you have stormwater collectors.
Underground. Yes.
Yes, you have stormwater collectors.
Now okay, thank you, sir. I think for me, if I had the power, I will contact the authority. I will raise that issue. I don't think I have that. And just make noise about it, because this country sometimes you don't want it to make noise and they listen to you. Okay, somebody else is raising their hand. Maybe after you are saying one. I know the problem of Japan. There is supposed to be an aeration tank somewhere. That aeration tank will now connect to the closest manhole taking water to Edu treatment plants. You know, Abuja is only 25% done, but a lot of things have gone wrong. So let me hear from Musa before I go ahead. Go ahead, sir.
Yeah, okay. Morning, sir. I want to add up on the issue of the sewer, but the sewer can be designed as combined sewer to carry both. Am I right? So could it be possible?
You're right, sir. We are coming to that, but let me say.
Okay.
Only in developed, in highly optimized countries, I can have that, because it's very wrong. It can lead to a mistake. What they do is this. They have what we call dry well. Even when they have such system, it's rare. As I said in my beginning, it's only about 10% of countries that practice that, or even less. And it's in big cities where they don't have space. You can have a combined sewer that during dry weather flow means there's no storm event. What is flowing in that sewer will be sewer, and it's going to wastewater treatment plant. Once storm starts, they introduce what they call bypass. Once storm starts, the water will bypass to a holding pond. It doesn't even go directly into the open stream. It goes to a holding pond where they apply minimum treatment, and the up one that might have been treated after 2-3 days, they will discharge it into the open stream. Maybe the BOD might have come down to, let's say, 15-20. Then the sludge at the bottom will now be moved back into the wastewater treatment plant. So for me, as at this point, forget about the idea of a combined system, even though it does exist. But it requires a lot of management skill, a lot of technology, and the presence of holding pond, treatment plants, proper sedimentation tank, aeration tank, which we simply cannot implement.
Okay. Yeah. I guess it's so complex. And
yes, God bless you. That's the word. Yeah. In theory, there's a separate system and combined system. But combined system is just a fraction, very minute. Maybe places like New York City or New Jersey, London. Okay, some special areas they can implement that. But for down here in Nigeria, we lack the capacity, we lack the knowledge, we lack the skill, we lack the infrastructure to implement it. And that's what Engineer Oni is talking about in Guzape. What is happening there is just, wow, I can't believe it. So another person raised his hand.
Yeah, good morning, Engineer.
Yeah, good morning. Maybe
please, I just
let it not be much. Yeah, go ahead.
Yeah, I want you to clarify something.
Okay. Now, introductory foundation. So, but there's a lot of calculations and formulas and everything. So this is a typical catchment where you have I say element of urban drainage systems. Okay, so if you look at it, you see there's pumping station, there's sustainability urban design for storage and infiltration. There's a sedimentation tank, there's a storage tank, there's a combined sewer overflow tank, and there's a combined sewer overflow. So these are all systems that make up the urban drainage. So if you look closely, you see that as the water is coming here on a separate system, it simply comes and goes into the wastewater treatment plant. On the combined system, you see the separate system coming, then you see the stormwater coming, and two of them passing through here, through an overflow structure, and they go to the treatment plant. So ideally, what this thing is just telling you is that sometimes your storm will just flow straight into the open river, open stream, okay? And then other times, your for the combined system, the sewer network will go through some kind of throttle structure that will separate the two, so that the contaminated ones that requires a lot of treatment will go to the wastewater treatment plant. So now, these are just some of the definition we'll be looking at. Okay. So here, for the stormwater, based on a code, German Association of Water and Wastewater, 1998, which is just the same thing. Last week, I told us about a universal formula that we'll be using to for anything hydraulics, and I said that Q, discharge. Sorry, discharge. Yes, in water recirculation, we say discharge is equal to AV. I say this thing can also be CIA, where C is a factor, a coefficient. So that coefficient, we call it peak coefficient of runoff. For today's course, we'll call it coefficient, whatever, coefficient of runoff. If you don't want to call it that, you call it peak coefficient, or simply call runoff coefficient. Yeah, also call it runoff coefficient of runoff or runoff coefficient. I mean, that's what it means. So what this factor is, let me explain everything first. Enumerate everything first. So then I, this is for storm. Storm. I is your intensity of rain. Of course, which you have to use the maximum probably flood, maximum probably runoff. The maximum anticipated rain is what you use for your design.
More precipitation.
Then the A is the area, which is always area. If it's for pipe, it will mean the cross-sectional area, okay? But for storm, it will mean the spatial area, right? The spatial area, I mean, spatial is spatial, I mean, the area of the land. So if you want to do the quantity of storm with water coming from your plot of land, 1,000 square meter. So it means this A will be that 1,000 square meter, right? Good. Now, this C for water recirculation, we say is 2, which will take care of losses, so a whole lot of things. But in this, our C now, this C, which is a runoff coefficient, is dependent on many factors. Okay, it depends on the area, north, south, how intensity is. But the major area that it depends on the slope of the area, number one. Depends on area. It depends on what we call land use. It also depends on the hydraulic or the material of that area. There are some places that have clayey soil, and that's why you see erosion in the southeast. I'm in Enugu as we speak, okay, for something. Now, why you see some of these areas being erosion is because the amount of runoff is too much. And why is it too much? Because the underlying clay materials does not allow water to percolate. When water falls on the surface, we have different levels of percolation. We have deep infiltration, we have surface runoff. It is after you have had deep infiltration, shallow infiltration, that the remaining amount of water will constitute runoff, will flow inland. So some of these areas like in Enugu and all these places, they have a lot of clay materials as their soil. So when water falls, you see the whole water flowing on the streets because the clay and silty materials have a porosity of 10 to the power minus 8, 10 to the power minus 10. In fact, some silty materials that they use in dams as core of dams have materials, the size of materials in the range of 10 to the power minus 12. The normal one you call sand, one used for construction, coarse fine aggregates, they are 10 to the power minus 4, 10 to the power minus 2. Okay, so they have high hydraulic conductivity. High hydraulic conductivity means once water falls, all of them will just go into the ground. Okay, and then they will flow as under surface water, thereby not causing erosion, not causing havoc. But in some of these erosion-prone areas, you find out that the problem is that the land, the soil, the underlying soil will refuse to take those materials. So a function of the material to slope, and the slope is also a factor. If a place is like a bed, a basin, when water falls, the water will just stay there, just impound there. It can't go down. Okay? So this C is it takes into consideration those factors that will make you not to use the A maximally, that will make the contribution of runoff will not be 100%. When water, for instance, let me give you an instance. The roof of your house has a runoff coefficient of 0.95. The runoff coefficient, by the way, varies between 0.1 to 1. That is the range. So when we say coefficient of runoff, it is between 0.1. So the more resistant you are to water infiltration, the higher your runoff coefficient. No material is 100% impervious, even though there could be, but the assumption is that no material is 100% impervious. So like some roofing sheet, like aluminum lamp span sheet, we can say it's between 0.9 to 0.98. I'll show you the table, have the table. Okay? It just simply means that virtually all the water, if this factor is 1, it means all the water that falls on the roof will constitute runoff. Okay? So it means that when you are doing your CIA, C will be 1. And once C is 1, it means A is A. But C is meant to reduce the area of A by considering the land use of A, considering the material makeup, the hydraulic conductivity, and then considering the slope of the land. Now, garden has a runoff coefficient of 0.2. What it means is that only 20% of every water that falls on the garden will flow overland, while roof is 95%. Okay, so this 95% means 95% of every rain that falls on the roof of your house, 95% of them are entering your drain. They are going into your drain, right? So if you are to calculate, you just multiply the area of the roof, multiply by 0.95, then multiply by the intensity of this rain that is coming. And of course, that intensity of rain, depending on your locality, people in Lagos, you have like 140 millimeter per hour, 150 millimeter per hour. Those in Brunu, they are getting like 70, 80. Okay, those in Abuja, we are having like 120. Okay, we are having, is a range anyway. I'll give you the material now. Those in Abuja, we're having between 90 to 140, depending on the long period. I'll still come to that. Depending on the maximum allowable flood. Okay, because you don't pick any value. You look at the one that is the highest one within 10 years, within 5 years, within 25 years. And that's why you are hearing 5 years return flood, 10 years return flood, 50 years without flood, and then the big one, 100 years. Nobody does 100-year design in this part of the world because it's simply not a good political decision. People will just see you as being overly expensive. So garden will be like 0.2. Then some garden, in fact, it's a range. Some gardens are even 0.1, which means when water falls in a garden, it means that 10% of it they will absorb. I'll still come to that. Some will evapotranspirate. Others will constitute deep percolation, and others will just come to the surface as runoff. So look at it. Let me look at it here. So, okay. Look at it. Once rain falls, for instance, I'm not sharing my screen. Once there's a runoff generation, how does runoff generate? Now, this is rain. This whole block, this rectangle, is the quantity of water that have rained in this catchment. Some will drift away. Some will evapotranspirate. In other words, the plants will absorb it and then give it out through their leaves. Then it will first do wetting. It will first wet the ground. When rain falls, sometimes rain will fall. It won't generate. There's no water in the drain because it is just wetting. So after wetting, it will now come to deep storage. Then some will infiltrate into the soil. Some will infiltrate deeper and go and constitute the unconfined aquifer of the groundwater. Then only a percentage will come as runoff. Only a percentage will constitute runoff. So this is the percentage you're going to design for. So why are we moving from this big rectangle to this one? A factor that will help you to come about this is the coefficient of runoff. So the coefficient of runoff will now take care of all these other values and then reduce it. So coefficient of runoff is like a reducer, and that's why it's between 0.1 to 1. So most times it is less than 1. So it's reducing your area so that the other component will will represent the ones that are infiltrating, that are wetting, that are evapotranspirating, and so on and so forth. So here, I think that I have to leave this for now. There's a word I would like us to understand, and that is called permeable areas and impermeable areas. The area that will constitute runoff is the impermeable area. Is the impermeable area that will constitute runoff. The permeable area will allow moisture to depercolate or infiltrate, while those impervious area, okay, some people call it paved areas, are the ones that will constitute runoff. So here, the catchment area will be represented as ACS, catchment area, okay? Then ACP will be all the paved surfaces of the catchment area, including runoff. Then ACMP will be some of all unpaved area of the catchment. So the degree of paving now will now be, which this degree of paving is just like the runoff coefficient. It will now be the area served over, the area paved over the area unpaved. Don't worry, we'll explain that further as we go deeper. So what is the implication of this? He said that constant rain does not generate constant runoff. It's a maximum runoff occurs only when, after all initial losses, you see, I've seen it. So maximum runoff will only occur when after all the losses are enumerated, which is wetting, depression, storage, etc. After they have been taken care of, then runoff will come. And after the runoff, you will now have the discharge you're going to design for. So he said that higher degree of paving determines higher runoff. So now this is the point. If you go to rural areas, the villages, you find out that everywhere is just bush, land, soil. It's hard for you to hear of flooding in sometimes, sorry. Okay, it's sometimes because when it rains like this, within 1-2 hours, everywhere is dry. But come to the city centers, come to central area after a rain event. Everywhere you will see, in fact, it's after the rain that you see the runoff. Because why? Everywhere is paved. There's interlock everywhere. There's concrete everywhere. There's quota everywhere. There's roofing everywhere. Okay? Sometimes these people don't follow the master plan because the master plan will tell you that you can only build 50 to 60% of your land mass, and at least 20% of it must be green, must be soft landscaping, which is like garden. Oh, I remember those days we came to Abuja newly. If you take your drawing to development control or to development authority for approval, if they didn't see enough space for water to percolate, which is in other words, they didn't see landscaping, they will not approve your drawing. Why? Because if they allow you to use concrete everywhere, then the runoff you will be generating will be so much, okay, that if every other person follows your design, then the drain sizes we have already designed for the city will be overwhelmed. And let me tell you, for those of you who live in Abuja, I'm not an authority, but I know this is what I project. Those of us living around, even Lugbe now, Airport Road, and those Lokogoma areas, I'm sorry to say, except FCDA intervenes or except the authority comes to your help, flooding will be an issue. Because development is not being regulated. Everybody builds his house and he puts interlock. Nobody is planting garden. Nobody is having open spaces for rain to percolate. Then the few areas that are for drain, that are green areas, estate developers will go and build land. Will go and narrow the river, narrow the stream. Even where they're not supposed to build land, because they have bought the estate, they will take up the green areas. This is wrong. At the end of the day, you are constraining the runoff part, the runoff. And what will it do? It will overflow its banks. And when it does, of course, your house will be in jeopardy. So, and except they start to do some demolition, I'm sorry, but, or, Nigeria will allow people to build before we tell them they are wrong. The time they are building, nobody will tell you. It's when you are finished building, and someone will not tell you that you are building the green area, that place is floodplain, and what have you. Okay? And this is real. If people build in floodplains, and that is the problem. Now, I don't blame them because floodplains are cheap. Places like Port Harcourt, all those riverine areas, before government comes and starts doing something. Okay? Like in most places you have in far north, KB, Jigawa, you hear of flooding, you'll be wondering how. It is because poor people, let me use that word. Even in the US, places like New Orleans, okay, poor people always go to reside in the floodplains because those are the places that are cheap for them. And unfortunately, that is wrong because once there is overflow, the stream overflows, or there's big runoff coming upstream, then when it comes there, it can't constrict itself again. That means it will overflow its banks, and that's when you see killing people and submerging houses. Okay, I think we've said much about that. So this is just storm. So how do you calculate storm? Our M in every hydraulic system, like what we're doing today, is for you to get your Q. It is the process of getting the Q that might be cumbersome that will now involve a lot of what I call hydraulic gymnastics. Okay, you do a lot. Like for instance here, your runoff coefficient or your runoff discharge is now the rainfall intensity multiplied by the catchment area multiplied by what we call the runoff coefficient. So all these things you see here, I want you to see it as CIA. Where is the C? This is the C. Where is the A? This is the A. This C and S simply means catchment area, sub-catchment. Because when you want to get the total runoff, you will get the total runoff based on catchment 1, catchment 2. Okay, so this is like area of catchment sub. So if I have Abuja, if I want to know the total runoff coming out from Abuja, if there's anything like that, I would say catchment Wuse, catchment Jabi, catchment Garki. Okay, and why I do them differently is so that I'll factor in their land use. Remember last week, that land use will give me an idea of the number of persons and what those areas are meant for. It has a place, it has a role to play. Then this RODN is one word, and that's your eye. That is your eye. And that eye, this RODN simply means the rainfall, a function of the duration and the return period. So this N is like frequency, which is the inverse of return period. This D is the duration. Every rain has a duration. 10 minutes rain, 15 minutes rain. For now, you use between 10 to 15 minutes, and I'll explain why. You have to use those two values. Then R is the rainfall intensity, which you read out from charts. There are charts and tables that are meant for that, and I'm going to give us one developed by the Federal Ministry of Works, Abuja. That's what we are using for now, because that one has been able to capture the rainfall intensity of every city in Nigeria. So then this symbol, I don't know what you call it in Greek, is the C, which is the coefficient of runoff. So this is the universal formula for every storm flow. It is the intensity of rain multiplied by the catchment area you are talking about, or where the rain is falling, then multiply by the runoff coefficient. He said, but for a given surface, the ratio between precipitation and runoff depends on the rain intensity and varies over time. That's exactly what we're talking about. It has some temporary factor. We talk about temporary and spatial extent or partial factor. Runoff coefficient can be given only for certain conditions. We need different values to solve specific problems. Example, mean runoff, peak runoff, mean runoff. I'll explain all those things. So now, this is nothing. Peak runoff coefficient is this over this. You can just forget about that for now. So now, if you have different catchments that have different runoff, it means you the average. If I come to a place like Gariki, there are some places that are roof, some places are road, some places are residential areas, some places are gardens with different runoff coefficients. So I need to use what we call mean weighted average. There's mean weighted average is like an average, but average is not a good representation of what is happening. Average just gives you an average value, but the mean weighted average will give you based on the component that have a higher weight. You have 10 naira, I have 20 naira. Our average is 15 naira. That is even wrong. Because we that have 10 naira probably can only afford 10 naira. But you that have 20 naira can afford more than that. So the average of our wealth cannot be. Because I need to factor in the one you put in other banks. So I'm trying to use this to explain the difference between the mean weighted average and the normal average. A normal average is total sum divided by number. But mean average is the sum, the sum multiplied by the number, and then you do it sequentially, and then later you divide it by the total number. So that's why you have the mean average of this I catchment multiplied by the average of catchment, multiplied by the plus the one for B, multiplied by B, multiplied by C, and so on and so forth. We are all engineers, we understand what I'm talking about. So to calculate the overall runoff coefficient of a catchment, the individual values can be weighed according to the percentage of each surface type. When the drainage system is planned for future developments, the percentage of each surface type is unknown. The expected distribution of surface type can be estimated based on land use. Land use has come again. Residential area, mainly one family, apartment block, blah, 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 industrial area. When we are doing development, we don't know which area will be paved and which one will not be paved. But if we understand the land use, it will help us know the degree of paving of each of the areas. So I told her that the runoff coefficient depends on many factors. So if you look at this place, to start with, let's say we're designing for a storm event of a return period of 2 years. The frequency is 2 years, or it's less than 2 years, and the duration is less than 15 minutes. What does this mean? If you want to pick a value for your rainfall intensity, you don't just pick any value. It depends on what you're designing for. You can decide, you don't just on your own decide to pick 5-year value, 10-year value, 15-year value, or 25-year value. No. If you are designing something based on a place that has high insurance, let's say I'm designing a city center, I'll use a return period higher, very high. But if I'm designing for a local area, rural area, I'll use a design period that is low. Then if I'm designing my system to withstand normal storm, I can use 2 to 5 years. But if I'm designing to withstand flood, then I'll be using like 20, 25 years. So, you see, values are higher than annual long mean. So that's by the way. Now, another factor that influences your mean runoff coefficient or your C is the slope. So, and the type of material. You can see here, asphalt. You can use asphalt. Asphalt has a mean runoff coefficient of 0.9. It means that if water falls on asphalt, 90% of it will flow into the drain, while only 10% will escape. Gravel is 0.7. So you can see that grass paper, where is paved, if you plant grass in a place, the runoff coefficient is 0.15. So the area contributing to the runoff will be reduced by 50%. Reduced to 15%, sorry. Then this is place that have high slope. For areas that are unpaved, that are flat, look at the runoff. The runoff is almost 80%. Because flat surface does not produce maximum runoff. No, someone say is runoff coefficient the same thing as manning runoff coefficient? It's part of it, but it's not exclusively manning runoff. It's part of it. That's the manning runoff. Manning N is talking about hydraulics, the roughness of the area, which is also part of what we're saying here. Okay. So you can see type of pavement. You can see, if I may ask, which of these will have the highest runoff? Can somebody ask me? Which of these will produce the highest runoff? Followed by which one? For me, I think here you have asphalt, left and right, produce the highest runoff. This one too produce a lot of runoff. This one too produce a lot of runoff. This one too produce a lot of runoff. But you see this one, I don't think it will produce a lot of runoff. Even this one. So that is that. Now, what this place is talking about is also to show you that the more slopey a place is, the higher the runoff coefficient. Like this one now, this chart, if the slope is less than 1%, you can see that for a rain intensity of 0.8, here is about 80% degree of paving. But here, 80% is higher. So here is one is 1 to 4, while here is less than 1. So the idea is just for you to know that there's an influence of slope on the runoff coefficient. Okay, so this is it in tabular form. In tabular form, okay? Depending on the degree of paving, if the place is 80% paved and the slope is less than 1, then if the rain intensity is 100, it will reduce it by 4%. and based on still 8, 70. But if the place is between 1 and 4 slope, the thing is no longer 0.64, it will not be 0.76. Is that understood? Okay. I'm bringing my time to discuss peak runoff coefficient so that when we start to do calculation from next week, you won't be lost in any way. So this is what peak runoff is a function of the intensity and every other factors. So these are the symbols we're using. These are the symbols we're using for this. Then for the separate sewer, solitary sewer is simply the dry weather flow. This is dry weather flow plus QRDW is what we call the infiltration water on dry weather flow. So here, if you look very well, this QRDW is those extra rain that usually fall and enters the sewer system. If not, Q separate just only Q dry weather flow. Dry weather flow, as I said before, is that period when there's no rain. So what is flowing in the sewer will only be what is coming from your home, will only be foul sewer. Okay? So that is dry weather flow. But once there is a storm event, there are some other small water that comes into the system, either through breakages or through something, just like our engineer talked about, Giuseppe. There will be 1 or 2 neighbors who will connect their storm water into the sewer. So this is meant to take care of such people. It's like a safety factor. Why the stormwater sewer is just QR, and we'll discuss QR. QR means CIA. We'll discuss QR. So this is just QR. But in this case, it is QDW, but plus small infiltration water. And in the combined sewer will now be the dry weather flow plus the runoff flow. So dry weather here is representing separate system, while the QR is representing the other system. So let's talk about hydrology a little bit. This is the water cycle, what it looks like. Waterfalls, some runoff, some discharge, some infiltrates. Precipitation can be snow, hail. The formation of runoff start with wetting. After wetting, evapotranspiration, filtration, and so on and so forth. Then the coefficient of runoff is also there. So anywhere you see D represents duration of rain. A rain can be described by each element. And what are those elements? By the duration, every rain must have a duration. The height, D, in millimeters. The intensity becomes millimeter over meter. So intensity is depth over duration. The frequency, as I said, is the inverse of the return period. In the past, to get your rain intensity, you simply multiply a factor of 167 times the intensity. But that is no longer being used now. So, further, this is some quantification of rain. This is what an IDF looks like. IDF means intensity, duration, frequency curve. From here, you can read off your intensity. But coming to that, I'll bring the Nigerian home. So this is the formula for intensity in the, okay, question. Okay, Chinedu and Ademoyo. Adeyemo. I'm speaking like the Nigerian. You have a question or is it a mistake?
Yeah.
If it's a mistake, you just click on it again.
Hi, sorry.
Sorry, are you happy to go to I think the third page from this one? Yeah, there. So, sorry, are you happy to describe the frequency again? You said N equal to I over A. What is A?
Where? Sorry, sir.
Yeah, frequency N is I over A.
A is the,
yeah.
A is the annual return period.
Annual return period. Okay,
yes,
that's right.
Let me explain to you what it means.
I was just going to talk about if you're happy to include it in the slide as well. Some of us might not be able to.
It's somewhere down the line.
Okay,
this is what
thank you
means,
very much.
And this is very important. As engineers, as designers, who do design, you must use probably you use the worst case scenario, the highest expected worst case scenario. That's just the word. So in storm events, we talk about probable maximum flood. You'll be hearing about it. Probable maximum flood. In other words, if you're doing your design, you're not interested in all those small floods that comes June, July, August. No. You're looking at that one that comes once in a while and causes problem. I will explain again. When we say 5 years rain or 5 years return period rain, what we're trying to say is that what is that maximum rain, that highest rain that will fall within 5 years? What is the value of that? So if I use that value to do my design, it means that in the next 5 years, if that storm should come, my design will sustain it. So in some places, if you want to design something like a dam or something, they will ask you to go and do study and understand in the last 10, 15 years or 20, 25 years, what is the maximum rain that's ever fallen in this place? That is the value you're going to use. And you can do these things through modeling, you can get them through modeling. So now, if I said I'm using 10 years as my design period, the frequency is now 1 over 10. And what is 1 over 10? 1 over 10 is 0.1. So it means that the frequency or the probability of that rain occurring is just 0.1. Okay? So the higher the frequency, the lower the number of years. The higher the number of years, the lower the frequency. So two of them can be used interchangeably. So that 0.1 means that it will only, for this rain to occur, it is like 10% chances. But at the same time, that is the rain that I need to do my design, so that my design will be optimized. Okay, the second person that raised his hand, are you okay now, or you want to ask for something? Okay, that must have been a mistake. You can just click click on your name and lower your hand again. Okay, I've done it for you anyway.
I'm sorry about that.
Okay, so this is classification of rain is for nominal design. When we say a weak rain is a rain that has intensity of less than 7. And now, if you do the calculation, it translates to about 650 millimeters per hour per hectare per annum. Moderate rain is between 7 and 21. Heavy rain is greater than 21. Okay. So the rain intensity, this is an old formula. These days we use table and charts. And that intensity is a function of the rain intensity, the rain duration, and the frequency. But these days, as I said, we've moved over to table. Yeah, you have a question. You raise your hand. Your hand is raised. Okay. Maybe it's a mistake.
Go back to the last slide where we're talking about the frequency. No, not this one. Not this one. Yes, here. No. Okay. Yes. Okay. The rain intensity. You know, this formula that is there. You said there is no longer in use. So
yeah, now we use table. Now we use table charts. I'll bring it up.
Oh, okay. Okay.
These are the world is moving. These are old formulas that are very cumbersome, very complicated. Even this one too.
Okay.
These days you just go to table. You read all these values, and I'll show that table. shortly.
Okay.
Okay.
Thank you.
So this is a case study. If I'm designing now, when I say arrow 15.1, this arrow 15.1 simply means the duration of the rain is 15 minutes and the frequency is 1. This frequency 1 now, what this one means is that from my experience, I know that this is ordinary storm, ordinary drain, normal drain. Because normal drain, we expect that the rain will fall at least once in a year. But other higher values means that the rain will fall once in 5 years. So if you say 5 years, it means the rain will fall once in 5 years. If we say 10 years, it means the maximum rain that will fall once in 10 years. So this one means 1 in 1 year. So it's a normal rain. It means within a year it must fall. That magnitude of rain must take place. Okay, so there is not say then 15 minutes. Why do we use 15 minutes as our rain intensity? Let me use a common sense. If I drop, let me use a chart and explain it. If this is a catchment, and here is drain, maximum runoff will only occur when all these places is wetted, and when the distance of travel between this place and this place is no more than 10 to 15 minutes. That's just what it means. Now, you don't need to ask much questions. Later, after the class, you can calculate. What we're trying to say is that once it starts to rain, how long does it take the water from the highest distance in my estate to get to my front of my house? If that rain is more than 15 minutes, it will become Lagos rain. Lagos rain it will rain all day in Lagos. You won't see any flood. In quote, I'm just being jovial. I'm joking. Okay, but you see some rain in Nifo, in Benin, or some rural areas. Within the first 15 minutes of that rain, you will know whether there will be flooding or not. If the rain is so intensive, within 10 to 15 minutes, as soon as it stops raining, you see flood coming. So 15 to 10 minutes is like a guide. We cannot wait until the rain will fall for 1 hour. No. If you collect your value, that's why how many of us have listened to CNN when they are predicting flood? Once they have measured their rain gauge, and in the first 10, 15 minutes, and they got like 100 millimeters of rain, they will tell you there's going to be flooding. That's how forecast takes place. And I can do it. In the first 15 minutes of rain, I know that there's a high tide. I take the measurement and I want this to rain. I can predict for you where we rain. And then based on the geography of the area, I can tell you where the flooding is going to occur. Of course, it's going to be downstream, but where in particular in downstream. So that downstream will be, I will now check what we call travel time. Travel time of the rain will give me an idea of where the rain will start to cause problem. So people who predict rainfall, predict all this kind of thing, or what they call early warning system. That's how early warning system occurs. NISA and all those agencies, how do they know? They can tell you that Lokoja will be flooded. Because if I watch the rain that has fallen within my catchment, and I look at the level, then if that rain moves from Abuja with that intensity, and as it's moving, it's picking tributaries, it's adding value. By the time it gets to Lokoja, it has become a flood. I will measure the distance, I'll measure the time of flow, and I'll tell you where the thing will hit. I mean, that could also be an idea of how they predict all this typhoon in the US. They will tell you exactly where it's going to hit, because it is the travel time, it is the frequency. If we didn't see anything within the first 15 minutes, I would say, forget about it. This way can't do anyhow. Or if I see something within the first 15 minutes, which is the maximum travel time, I allow the drain to cause problem downstream, then I can tell you what is going to happen. So that's what that means. So for instance, in Germany, from their table, from their chart, for 15 minutes rain at intensity of, at a frequency of 1, or the time period of, of 10, the value is between 130 to 90, between 190 to 130 liters per seconds per hectare. I'll still analyze this. So he gave us the one for Stuttgart as 126. Okay, but this is the range. So that is that. Okay. Remember, it is only applicable if the duration of the rain is less than 150 minutes. And the frequency is between 4 and 0.05. So I've discussed this before. Peak runoff, how does we come to peak runoff? First of all, there'll be drifting, there'll be wetting, there'll be evapotranspiration, there'll be filtration, and the remaining one will now be what? Runoff. And that runoff is what we call peak runoff coefficient. And it depends on many factors, which I've explained also. Percentage of the impervious area, surface type of pavement, the slope, the rain intensity, and the duration, the type of soil and vegetation. So these are the things that will make your rainfall intensity to either be close to 1 or close to 0. It can never be 0. So for a slated roof, it's about 0.95. For a gravel part, it's about 0.15 to 3.0, because a gravel part, once water rains, is going inside the ground. So how do we do house connections? This is I want you to have this in your mental picture. What you have on your screen. Wow. Yes. What you have on your screen, I want you to see what you have on your screen as a mental picture. Okay. Now, both for the sewer and for the storm. You know, we are still on storm, but this is the same thing from a sewer. Now, this is water. This is a house or property or a plot. You can see that water, whether it be storm water or sewer, will come into the central line. The one here will come into the central line. If you are now looking at it from in terms of the volume, you will find out that once it enters here, the intensity of rain is this height. The Q, discharge is this height. When it gets to this person's house, the water coming from here and the one coming from here, it will go up. When it comes here, it will go up again. By the time it goes down all here, it has already come to this peak. So as the water is moving downstream, it's increasing in value, it's increasing in quantity. Okay, so this one becomes house. This becomes your yard, of course. So all this one is the impervious area, because that is the area that's contributing to runoff. All the impervious area here, which is your roofing of your house, and the kind of material you use to pave your house. Okay, and then here is the sewer, and then here is the garden. And so this is just like have a mental picture of this thing going up as it's going downstream. So the sewer line will keep increasing, and so on and so forth. So once again, let's go back to the universal formula. Discharge is intensity times runoff coefficient times the area. This one is no longer being used. This is what we call time factor. And that's what I was trying to explain to you about time. So the time factor I'm thinking of, because if you are reading your value from the chart, you go for the one that's written 15 minutes. So time factor will no longer be there. Okay, you have a question, ask the question, sir.
Yeah, sorry, thank you. You said this formula is universal. Can it be used everywhere? Is it limited to Germany?
No, it's everywhere. That's CIA, sir. This is just CIA.
Okay.
CIA is universal. When we say German, it's British. Go to Europe.
Yeah, because the standard you're referring to in question is I think DWA.
198. Yeah, you can Google
198.
If you go to UK now, it's just the same thing.
Yeah, I think somewhere like the UK they use FEH standards and not into hydraulics and all of those.
The word I need from you is that what does the standard say is the UK rainfall intensity? That's just it.
Okay.
The area of a land in the UK and the area of a land in Abuja is the same thing.
Because sometimes you notice that people have different yardsticks or different coefficients.
And I'm telling you further that those lines are blurred. And I've given you an idea of the rivalry between France and Germany. If German says 0.98, French will say 0.97. That's just them.
Okay.
That kind of thing. So
Thank you very much.
It collapsed to the same place. So this formula here is CIA. The C is these two guys. We're going to converge them now. A remain A. I, they just use R to represent rainfall. When I call it rainfall, I call it intensity. It's the same thing, right? Yeah, the Germans call it R, based on their language. But here we use I, which is intensity.
Hello.
So here, yes. I can hear you, sir.
Yeah, the intensity.
Yeah.
I heard you saying, I heard you saying between 10 to 15 minutes.
Yes.
But I know in CIA, the intensity is referred to as a rate of.
Just hold on. Okay, Engineer Ibrahim. No, when I say 10, no, I say when you are reading. No, it's a function of D and N. So is a function. So if you are reading it off, you read it from 15 minutes, and then also read it off from the return period, which is 1. So this one, arrow 15:1, is like a guide. When you go to the charts, you look for where, just like we did, was it last week? You go for where there is 15. Okay, we did it in our cost engineering, where we are using interest table. So when you are reading from the chart, you go for the 15 minutes, then you go for the one that has a frequency of 1. Are you getting me? Is that when we're talking about designing a diameter? We said diameter is a function of the slope, the roughness, and the discharge, isn't it? So when you're reading from the chart, you should look at a particular slope. So in this case, you should be looking at 15 minutes. So at this point, let me show us what this highway design manual looks like, so that I will even send it now. Okay, I think let me go to Drive. Let me go to our Drive, my own Drive, and bring it and share it now. This is an important document from Federal Ministry of Works. Some of us have it, some of us have access to it already. For those who don't have access to it, let me share with you. It was developed by Koren and Federal Ministry of Works during the time of Mike Ononome. I think he paid a lot of money, and they were able to develop that piece of manual. For me, that is one of the first code and standards Nigeria has at this moment, as in indigenously developed, which, albeit unfortunately, we've not been able to publicize it because it's such a good, wonderful material that we can reference. But one thing I've also come to realize in Nigeria is that we are good in developing things, but we hide it away. We spend a lot of money and do research, and we just slot it out inside one director's office. Why those that are meant to use it will never have access to it? So let me see. I think it should be somewhere here. Wow. Okay. Just hold on, stay with me. Let me simply just go and upload it. It's a very important reference manual. I can recommend it for you if you're designing, because what people do in the past is that you go to river basins, you start asking them about their rainfall intensity and all those things, okay? And those things are really manipulated values you get. Yes, you're going to get manipulated value because somebody will just be in his office and be writing values. So this is Nigerian Code of Practice, Volume 1 and Volume 2. So let me upload it. It's in our chat box. Go to the chat box and download it. It's about 5 volumes. One is for geometric design of road. One is for this. So many of us have it. If you are within the corridor of infrastructure design.
Hello, Uche.
Yes.
This millimeter per hour, when do you apply it?
Why do I?
When do you apply it in this formula? Millimeter per hour.
Yeah, you apply it. You apply it and then convert it. Let me go back to the formula. That's a good question. Here, this value will be in millimeter per hour.
That's the I, isn't it?
The R, yeah, the I, yes, or R in German, yeah. Yeah.
Yes.
Then these two now, as I said, this one will be taken care of. If this one will be taken care of, then this one, which is the coefficient of runoff, will be based on the material it is falling, or based on the average coefficient of the area. I will do one case study next week. It will be between 0.1 and 0.9. Let me give you a instance. Currently in a place, like a hotel, where 60% of the land here have been used to build the main structure. The remaining 20% of the remaining area are asphalted. So what do you think is the coefficient of runoff of this building where I am? It will be around 0.9.
Yes, 0.9.
Yes. Now, if I go to my village now, everywhere is farmland, thatch roofs. What do you think will be the runoff coefficient?
Between 0.1 and 2.
0.1 and 2. Thank you. So, yes. But now, when you start your design, there will be a table. There will be a table that will tell you the value for everybody. In fact, let me shock you. Let's go online. You know, I always advocate. I'm the Google advocate. Just come here and say runoff coefficient of different materials. You'll be amazed at what Google will give you. So here we go. Okay, so runoff. Cool. Okay, look at it. Look at what it has given me. It's a runoff coefficient of roof, runoff coefficient of grass, runoff coefficient of, let me just say, table for different surfaces. Millions. Uncountable. Where do I start? So many of them. So if you now go, you now do the average of the different, because a catchment will tell you garden. There will be a garden. There will be a playground. Residential area will constitute only 20% or 30%. Recreation area will be 10%. Road will be 15%. So it's easy for you to compartmentalize. But let me just give you a value that you can just use. Just use around 0.6. 0.6, 0.7. It can't be more than 0.7. After all the mathematics computation, it cannot be. Okay, so look at this one now. Okay, see, he's telling me now, pitch roof, based on the rain intensity, you can see what it is, up to 0.99. The depth of rain is about 125. The average rainfall in Nigeria is 125, by the way, 100. It's only in Meduguri and some places you see 80. So this is the value in inches. So for flat roof, it is 0.96, the coefficient of runoff. For pitch roof, is 0.99 because pitch roof has a higher slope. Remember what I said? Then small sandy soil, look at sandy soil. 0.25. So you can also see, that's what I was telling you about Enugu. I came to Enugu and I was looking at their land. I say, wow, what a laterite. I was telling a friend as we were driving through, I was just seeing burrow pits everywhere, very reddish laterite. And I say, wow. I say, this is cool. I say, you don't even need to go too far to get laterite for construction or for road. But then I never knew the other side of it. The other side of it is that erosion will be commonplace here. Right? Because look at it. Urban soil, sandy soil. You can see they have different runoff coefficients. Right? Look at clay soil. Clay soil is what? 0.45. It means 45% of every water that falls on the clay soil will run on the surface. Whereas for a sandy soil, only 25% will run on the surface. So who is contributing more runoff? Is this man? So at least some of you now should appreciate why there is erosion in the southeast. It's part of it, gentlemen. You can't rule it out. Unless you're not a technical person, you should understand. And if I go to some areas where they have hard soil, like let's say Plateau, I don't know in other areas, I don't know anywhere in the southwest. If their land is very strong and is sandy, you know what I mean? Then erosion it's not possible. Because once the rain falls, it will just go into the ground. Because it's that one that flows on the surface that causes havoc. it comes with intensity, it comes with speed, and if the place is happen to be sloped, to have high slope, then it will come with a supercritical flow. And when it comes to this particular flow, what does it do? What does it do? Sorry, it will erode the underlying surface because it has a lot of energy. And if the Manning's end, the person that asks about Manning's end, if the Manning end of that surface is low, then it will just carry everything. So let's continue. So can you see what's in Google? So even though we just Google now have given us an insight on bending. And that's why I keep saying this. These 2 hours we are spending every Saturday, it's not something, it's more, but it is just to introduce you. And so when you see this kind of charts, I mean, this thing can be strange to you again. And this is just one. Remember, we saw like 1 million. So it means if I can spend 2 hours explaining all these things, this one is giving you range. It's giving you the range and also explaining to you pave, mainstream brick, blah, blah, blah. Oh, look at this, another beautiful one. So this is what you do as a designer. If you are designing, just copy this thing and put it in your calculation sheet and show it to the client. That's part of what, or you're the one you find in any of the standards. Okay. Oh, look at this one. Is even using it for stream design. Yeah, can you see it? So look at it. Say residential suburban. It's advising you to use runoff coefficient of 0.25 to 5. Where you have apartments, 0.5 to 7. I didn't see this before I advised you to use 0.6. So you can see that I've been justified. Playground, very low, because playground we know is always green.
Grass
And green. Then downtown California, 0.7 to 0.95.
everywhere is paved.
Everywhere is built up. And no space for. Okay, let's continue. Where are we again? Okay, this is where we are. We are still talking about drainage. I need to speed up. Oh, we can't do this now. We'll do it from next week. So this introduction, but this is just an example of what I just explained this morning. Okay, or let me just run through it. Okay, this is an area, 100 hectares. Out of this area that's 100 hectares, the impervious area is only 45 hectares. And this is the area that will contribute to storm. The population is 1,000. The flow of water consumption per person per day is 150. Infiltration water, which is unaccounted water coming from here and there, including the pure water I bought, taking it to my house, as against the one water board is giving me. Okay. Then time of flow, maximum time of flow is about 30 minutes. So we're going to do this next week, the calculation. So for the total sewer overflow, you see, this is the wastewater flow. That's for the sewer. If I'm doing the sewer, wastewater flow plus the filtration flow to give it to 2 liters. This will confuse some of us for now. So here, you will see talking about if you want to size what I told us based on another code. It's giving us this is the catchment. Water comes, it goes to the combined sewer overflow. Why do we call it combined sewer overflow? Is that when it overflows, the clean top parts of the water will enter the river, while the remaining one will go to treatment plant. After undergoing all the treatment processes, in order to reduce the BOD, it will flow back into the stream. Separate sewer. This is what the separate sewer looks like. Okay. The blue line is the stormwater from the roof, from traffic, from your yard, from surface runoff. Water falls. Okay. And it flows as a storm through your open drain or underground drain, which is usually made of concrete and is within 0.9 millimeter, 900 millimeter to, let's say, 2 meters or 1.5 meters, and some people use 0.600 millimeters. Some people in most estate developers use 600 millimeters without considering the extent of the catchment. So it flows to the stream. This thing is not usually available. Okay, but this is for developed countries. They will have something like what they call stormwater treatment tank. It's not like they are putting any chemical here. It's just that when this water falls here, the top one will overflow. The ones that are highly turbid is the kind of the sludge at the bottom will now be evacuated either with the hand or through another pipe, or will be taken and will be dried on the surface. Okay, then the separate sewer is now your domestic wastewater, and then domestic wastewater from industries. They will flow through a sanitary sewer or foul sewer or just simply sewer. Okay, after all have infiltrated, it will now, no infiltration, sorry, plus infiltration water will join. In Abuja, who is the engineer? Engineer from Guzape, the engineer from Guzape. Let me tell you what happened.
Engineer DG.
Engineer DG. The day I went to do water treatment plants, I noticed that they were complaining. This is a serious issue. But once it rains, it will distort their hydraulic balance. Those of us who are into wastewater treatment, the commonest method of treating wastewater is what we call the aerobic system. The aerobic system or the activated sludge system. Okay, where you make use of where you make use of bacteria, you build a medium, okay, and you build some level of bacteria within the medium. So once you build wastewater, those bacteria will eat it up and excrete carbon dioxide. They will be eaten off and so the water will treat itself. It's a different cause. Now, you must maintain what they call hydraulic balance, as in you have built that system over some months, over some years. So once a certain number of wastewater is coming, highly contaminated, that will serve as substrate or food for those bacteria. So once they are coming, the bacteria are eating them. Once they eat them, which is just like an oxidation reaction, because those bacteria are, I don't know the biological name again, but they are anaerobic bacteria. So they lack oxygen. So, no, I can't remember again whether anaerobic or so. So the idea is that these bacteria will be eating this wastewater. Once they eat them, the clean one will go. So what happened to in wastewater treatment in Abuja is that because of all these wrong connections that you talked about, once there is a storm event, rainfall event, the rainfall is supposed to follow a different system, which is the open drain. Well, because these people have done wrong connections, and the rainfall is now going into the sewer. So when it's raining, they will have food or wastewater coming. That instead of it to provide food for the bacteria, it will come and distort the hydraulic balance. Or sometimes it will even come and wash out the bacteria that they have built over the years, over the months. Meaning that they have to start all over again to build the culture. So what they do is that they will open their bypass. Yes, I've seen it live. And when I went there, I shouted, and they tried to cover it up. What did they do? Once it's raining, they will close their plant. The whole water that is coming, they will open the bypass. It will go directly to the stream. No treatment. Yes. And that is why, once in a while, you hear of cholera outbreak in some local communities. You'll be wondering. That is what causes it. Wow. People just live in ignorance. Once in a while, you hear that all those local communities, the world is so skewed that it's only the rich that are comfortable. Nobody cares about the poor. You find out that some local communities, some shanties, some outskirt communities, they'll tell you there's outbreak of dysentery, there's outbreak of cholera, there's outbreak of whatever disease, because their stream, which is the source of their water, have been contaminated by us. because we have done wrong connection that will distort the hydraulic balance of the treatment plant, and those managing the treatment plant, in order to avoid losing days and months of their hard work, we just open the bypass, and then the whole rubbish will flow into the open stream. Of course, some aquatic structure will manage to survive, but others might not be lucky, depending on what is coming. So that is why this sanitary sewer must be treated in the treatment plant for some few days, maybe 10 days, 15 days, by injecting oxygen. Some oxidation, you know, when I say the BOD, biological oxygen demand, is 400. What it means that you need 400 milligrams of oxygen per liter to treat 1 liter of that wastewater. So you bring it to manageable level, okay? Level where it will not cause harm, first to the aquatic organisms, and then maybe to humans who are living downstream and need it. For me, I'm not that with time, Nigeria will get to that place where if you empty the wastewater into the open drain, you will not only be penalized, but you should be prosecuted. So this is what the combined system looks like, which I said is not applicable in most times. The good thing is that at this point, there is a kind of structure, combined sewer structure, that is put in place to divert the wastewater, the ones that are highly contaminated, to the treatment plant to be treated based on the treatment steps. And then others are allowed to spill into the open river. So these are the advantage and disadvantage of each of them. Okay, for the separate system, just like the engineer said, wrong connections is possible. If you have a separate system, just like what we're having in Guzape now, because we have a separate system, wrong connection is possible. But in the combined system, wrong connection is not possible. But this is difficult to maintain. So we can read up this anyway, and so on and so forth. You can really understand all this one. Okay. So, any question? Yeah, I'll upload it after the class. I'll upload everything in our drive and share it. I'll share them. Don't worry. I'll do that. I'll convert them to PDF. Just give me the end of today. But I'll share it before we leave the class. The last 10 minutes of the class, I will share all the slides. Then the other heavy material. Okay, I will share some materials. Don't worry about that. Material is already somewhere there. Yeah, I'll just share the link. Okay, now these are advantage and some disadvantage of a modified system. I don't want to go into all this. Anything that we can really understand that I'm not interested in going through it. Okay, so that's the end of that slide. So we have finished these 2 slides. We have finished the slide on urban drainage. Let me close it. Then this slide on components. I think I've already said some of them. These are the components, what makes up a sewer network: Gola inlet, pipes, manhole, special buildings, and infiltration structure, and then wastewater treatment plants. So these are like the components of a sewer systems. Okay, sometimes you have a pumping station, but it's rare. Pumping stations are only found at the inlets of the wastewater treatment plants. Why is it so? Because sewage will flow by gravity. And when sewage is flowing by gravity, it means that there will be a head difference between the residential area and the treatment plant. Sometimes it can be 6 meters, sometimes it can be 12 meters. I have seen treatment plants where the difference between the head with the inlet of the wastewater and the treatment plant is about 12 meters. So you need to pump when it gets to the treatment plant, you will need to pump it up back again into the tanks, because flowing by gravity, it means you need to slope down, so it can flow very well. And the sloping must be done perfectly to avoid blockages, right? So the pumping station is always found at the treatment plants, and these are usually made of what we call Archimedes screw or screw pumps. screw pumps, because of presence of suspended solids, must be a special type of pump. Okay, mostly rotational Archimedes screw. You must have seen their picture online. You can see them. So these are some of the properties of the catchment and everything, and the type of pipe. Now, connection to sewer usually by a pipe width of 150 mm. That's what the standard says. So if you are connecting your sewer from your house to the sewer line on the street, the minimum pipe size is 150 mm, which is what we refer to as 6 inches here, right? Then the catchment area should be a maximum of 500 meters square for each gully inlet. So I think we can read this and understand all this. So this is an example of a gully inlet for storm. Okay, then pipe closed for wastewater discharge. It has to be a closed pipe. Only in few occasions you use dishes. The flow will be by gravity. Only in few occasions you see force pipe or pump system. Then the cross-sectional areas, they're usually circular profile. Some can also be egg, mouth, or rectangular profile. How do you determine the cross-sectional area? Well, it depends on the amount of wastewater you want to convey, the slope of the sewer, the variation in flow. So these are the things that will determine the kind of cross-sectional area you adapt. Please, the best cross-sectional area is the circular profile, round pipe. These are what those surfaces could mean. Then for sewers, constructing them, this is some of the ways and the methods and the tunneling and the what have you. Just like this one. So this is a sewer, a foul sewer or sanitary sewer being laid. There are different materials you can use. Vitrified clay, which is outdated, concrete, which is common, bricks, and then plastic pipe, and the advantage and their disadvantages. So for sewer layouts, this is more what the diameters are. This is what you should take precaution. You must use the shortest possible way. You must try and use the slope of the street. You must try as much as possible and use pipe sections of similar lengths. The point of changing the diameter of the pipe should be at the manhole. You must avoid constriction in the direction of flow. You know, sewer has tissue papers, human remains, different nonsense you can find there. So you should make sure that anything that will lead to blockage must be avoided, and so on and so. Then you must make sure there's no backwater formation, and so on and so forth. How do you arrange it? What is the depth for places people that have snow? It should be not less than 2 meters. Here in Nigeria, 1.2 meters is enough because we don't have incidents of snow. So these are the properties of manhole, how to construct them, what they should look like, and so on and so on. I don't want to go into all these things. This is 2 hours. I mean, in the next 2 hours, you can sit back and read all these things and understand them. So this is what that combined sewer overflow looks like. You can see this is the underground sewer of some cities. What do you need inspection chambers for? What are they used for? You can all read it off here. And everything here is self-explanatory. So this equation is what every engineer knows. Q equals to IV. AV. You know what V is, you know what A is, you know what this thing is. Then frictional losses, which these days we no longer use. And these are the formula we use for the other side. So these are just basically what we call GSTs in those days. So I think this is what an outfall is. Outfall is the point where the storm line enters the stream, open stream. It's called an outfall. Pumping stations are rare, as I said, but why do you need them and what can they do are all written over here. The types of pump, rotary pumps, screw pumps, the advantage and disadvantage, screw conveyors too. This is a motor. This is what a sewage pump. This is an example of a sewage pump. Okay, everything this is submersible anyway. This is a submersible sewage pump. The motors are protected with a sealed membrane. Displacement pump. This is what the Archimedes screw is. This is what the one I call the Archimedes screw. This is the one that is mainly used for wastewater. You know why they use this? Number one, it will save, it require less energy. Number two, there's nothing like blockage. Everything can be seen. Even if you're carrying human remains, it cannot block. So once the water comes from the city, this will be the level of the water. Why? Because it is being sloped, so it can flow. So there's a real tendency that it will have gone down at the point of treatment plant. So this screw will lift it up again, back to the grid chamber, and then it will undergo all the various treatment steps. This is a really large picture of the Archimedes screw. You'll find this in every treatment plant. Easy to maintain. So these are some properties of efficiency of pumps, which you can Google online, you can see them online, and even read them. Okay, that is all for now. The last slide, I think we've done hydrology, we've done sanitary, we've not done sanitary. So let me quickly go through that slide before I share. So these are the definitions. Yeah, that's good. Wastewater sewage is wastewater flow, is your dry weather flow or the daily water requirement plus infiltration flow. Please, this infiltration flow is just additional water that might come. So basically, your wastewater flow is your daily water requirement. What this formula is talking about. Okay, so dry water flow will now be the wastewater flow plus infiltration water, just to scale it up. And combined is now this one. So specific wastewater demand, for instance, we talk about the liter per capita per day, okay, which is what we use in water. You use it again in wastewater. So that is how to rate your input parameter for your sewer design. So as you want to design your sewer, just use the value you have used as your water intake, because that's why in some countries, as they are charging you for drinking water, they are charging you for wastewater. The same thing. You pay for both. Why? Because they expect you to also produce what you have taken. The rain intensity, which is for storm, is also, the formulas are here, and the different units they can occur are also here. So this example of wastewater demand, wastewater discharge for different countries. One thing I will tell you is that this is also equivalent to drinking water requirements. No difference. So you choose between 10 and 250 as your wastewater discharge per capita per day. Okay, then the daily one will now be population equivalent multiplied by that value you've chosen. This is exactly what we've done last week for water. So you can see that this is just the reverse of what we've done in the last 3 weeks. Okay, the difference is that you're taking water from tank to your house. This time, you need to take it from your house to the wastewater treatment plant. So that's just the reverse opposite of what we did. But the formulas, the methodologies are just the same. So wastewater production in Germany, average population of small trade 130. This. But it just didn't do the same thing for the water. So wastewater discharge into public sewer as a precaution. You should not discharge things that destroy the sewer line, that hampers the operation of the sewer system, or that diminishes the efficiency of the wastewater treatment plant, or that could impair sludge treatment. You should not allow any of these things to get into your wastewater. That's what this place is talking about. Then the ones going to the treatment plant, you should not also allow all these substances to go there, because they will distort. Some of them will even kill the bacteria. It's like allowing acidic material to go into your biological treatment plants. All the bacteria there that are meant to be your agent will all die. So this is the specific wastewater production for swimming pool, for school, for restaurants, which is just like the water requirements, if you look at it very well. Yes. So that is that. So the whole 3 slides, we've gone through them. So the next thing is from next week, we'll start our calculations and formulas and what have you. So quickly, let me convert some of them. I've started converting some of them, and I will share some of them with us right away. Any question? Question time.